All right, perfect. We made it a couple minutes. Sorry again about that. All right, so today we're going to finish up, hopefully, the slides. We'll talk about the electromagnetic spectrum. We'll talk about reflection. We'll talk about refraction. Those will be the three topics. Also, you all hopefully saw my email about the grades being basically up to date. So everything I have is now in our discussion, in our web courses. I grabbed all the discussion grades that existed as of yesterday, I think is when I did it. I grabbed the clicker questions. I adjusted the clicker questions. So if you saw your score was fairly high, that's because, remember I told you all, if I asked 100 questions, I would grade it out of 75 points. Because I give you all 75% just for doing the problems. The other 25% is just, if you get the problem right, great, just bonus points. And then I moved all the quiz grades over as well. So all of that stuff is in there. So whatever, and your multiple choice scores are in there with the curve. Every grade I currently have is in there. So the grade that it currently shows is your grade in the class, given everything that's graded. Everything that's in my control. Free response, we're waiting on those. Those will be 20% of the last test. So it shouldn't change things too much. If there's any discussion sections that get graded, basically anything at this point that isn't there for reasons outside of my control, that will not change the grade that much. So it's a pretty good indicator of where you're at. The only thing to really keep in mind at this point is if you haven't done discussion sections, you can still submit those for late points. There was no necessarily deadline on that. That was just if they got in late and you showed up, it was 75%. If you did not show up and you submitted late, it's 50%, but hey, it's not zero. That's really the only thing that could be made up at this point, as far as grade points are concerned. So, I guess the other thing is, I've told you all, the final will replace your lowest test grade, which it will replace your lowest test grade unless that hurts your grade. So at worst, your grade stays the same. It doesn't change in your test grades. At best, it replaces the lower one. If your final is worse than the other two, I'll keep the other two as is. Whatever helps you the most, that's what will happen. All right. So there you go. Done and done. Any quick questions on that before I get into the stuff today? Yeah.
We have to take the final for a favorite or final grade?
Yes. Because the final is worth 35% of the grade. So the final grades that haven't, assignments that have not happened yet are not factored into your grade. So if you take the final, if you don't take the final, it'll be a 0, and that's, I believe it's 30%, let me double check. 20% of your all's final grade, I forget the exact number. Syllabus says 20%. So that would mean if you do not take the final, the highest grade you get in class is an 80, which would be not ideal. So yes, you do have to take the final. The logic being the final has a few concepts not covered in the other two tests, namely what we're covering today and next week. And it kind of sees if you remember everything by the end of the course, because it's cumulative. My logic being by the end of the course, hopefully you haven't forgotten everything already. That would be not ideal. So yes, please show up for the final. Okay, great. Also, we do not want to try to do makeup exams for the final. I've had that for the other ones because the final is 2 hours and 50 minutes, and if needs be, it would just be a nightmare to do. Let's just put it that way. Currently, I've been doing them in my office hours. Well, there aren't office hours after the final because we're done. So, if you're deathly ill, if stuff comes up, shoot me an email, we'll figure it out. But I'm desperately hoping we don't have to do any makeup exams for the final because it's just, logistically, it will be a nightmare. Yeah?
How many discussion sections do you have left? Is week 10 it? Or
we have this week and next week, and that's it. So there's one more for next week. Do I have those questions yet? No, because that's not an answer. Yeah, anywho. So I will upload those as soon as I get them. Maybe you'll get lucky and I won't get them till late, and I'll say, oh, they're not happening because it's not my fault. No promises. But yeah, it's this week and next week are the last two discussion sections. So there's that. All right. Last class, we left off, I gave you the main points that was said, light's a wave made of electric fields and magnetic fields. We talked about the intensity of that light, which was the energy per second per unit of area, based on the electric field, magnetic field, and constants. And I'm actually going to change this. Intensity of light, which has units of energy per second per unit area. Close that up so that way it's more correct. We have the equation for that. Good news, that's not gonna show up in the final exam. So don't worry about that too much, that didn't make sense. Frequency and wavelength are inversely proportional. We have the equation C equals F times lambda. That is a very important equation to know. That's a classic when it comes to light. We learned that energy is directly proportional to frequency. I'll just quickly, actually I can type them out. So we had C equals F times insert symbol lambda. There we go. There's our beautiful Greek alphabet. It's where I live when it comes to inserting these symbols. Lambda is there. There it is. Great. Frequency times lambda, and then we found that energy was H times frequency. So pretty straightforward equations, pretty simple equations. H was a constant, F is frequency. And then all light travels at 3 × 10⁸ in a vacuum. In a vacuum, we're going to learn today that it does travel technically at different speeds in different mediums, but everything I was telling y'all before was in space. In space, regardless of the wave, they all travel at 3 × 10⁸. From light's perspective, it's always traveling at 3 × 10⁸, no matter what material it's in, but that's a whole different story. I'm not going to worry about that. I skipped a problem that I'm going to come back and do because it comes up in the discussion, and it's got some good... It uses 3 different equations, one of which was on test 1, so it's good for us to remember that, and then the rest are from what we covered today. So it's a good problem because it utilizes a few different concepts. Some today, some previous. During heart beating, the heart creates a maximum 4 millivolt potential across 0.3 meters of a person's chest, creating a 1 hertz electromagnetic wave. There's some current makes a wave, there it is. You all could not actually measure. I did a lot of Googling on this problem, so I grabbed this from the OpenStax book because I thought it was kind of fun. This would be, you can't really measure this. So you would not really be able to measure this. Whenever you talk about measuring frequencies and stuff, it is not using this wave. This wave is very weak. So anyway, that's just to toss that out there. What is the maximum electric field created? What is the corresponding maximum magnetic field strength in the electromagnetic wave? And what is the wavelength of that wave? And let me triple check. Yeah, it's working. Normally my webcam has a little light on it. It didn't, so I was a little worried. So what's our givens? We're given voltage, which is 4e⁻³ volts. We don't want to forget voltage. That is a scalar, not a vector. We have distance, 0.3 meters. You're going to see why I put that as distance. We report, whenever we see meters, that is so many different variables in this. It could be x, it could be r, it could be d, it could be... We have so many uses for meters and so many different equations. You're going to see why I'm calling it d when we get to our equations. And it creates a frequency. Hertz is always going to be frequency, so no worries there. Volt is always going to be voltage. It could be EMF, I suppose, if we're talking about magnetic fields. Great, so we have voltage, distance, and frequency. We always have the speed of light, so if you want to put that here, feel free, but, you know, pick your poison. Pick your poison if you want to put constants in your givens. I'll put it here just because we are going to use it. Step 2, what are we solving for? We are solving for the electric field. We are solving for the magnetic field. We are solving for wavelength. Step 3. The equation. So the first equation we're going to use is the relationship between the electric field and voltage. The relationship between electric field and voltage. I'll let you all see if you can scour anywhere in the recesses of your mind and see if you can remember that equation. If you don't, you'll have the note card, so it's not a big deal. You'll have the equation sheet. But it's always a good exercise. What is that equation? I'll give you all a few seconds just to think about it. The equation was V equals E times D. V equals E times D. We saw this when we talked about capacitors in particular. That kind of showed up there. V equals E times D. Rearrange that to solve for E. E equals V over D. Pretty straightforward if you know the right equation. Not a complex one, but kind of buried in the recesses of the equations we've done in this class. So we're going to be able to get E. Great. Straightforward, plug and chug. I want you all to see the next two equations we're going to use are from what we've learned so far. So again, spend a few seconds. Think if, once we solve for E, we'll have E, we'll have E, we'll have B, we'll have D, we'll have F, we'll have C, and we need to solve for B. See if you can find some equation that has a B in it where you know the other two things. See if you can rummage through the other equations and find one with B and two of these other variables. I'm going to give you all a hint. It's the first equation I gave you when it came to this stuff. Yeah. Yo, did you find it?
This is from yesterday?
Yeah?
Is it I average equals CB initial squared over 2 U naught?
So that one has E and it has B, but we don't have the average intensity. So that one you would need the average intensity. But that's a good guess though. It has the other ones, but that's so we can knock that one out.
C equals E divided by B.
C equals E over B. We do have all the ones there. So we can't use this one. Now, I suppose you could actually, you're correct, you could actually, you could use the E there and get B from that. It's a good point. So you could actually use either one. He raised a good point. You could use,
Even if you don't have I average?
yeah, you could use the one he mentioned because, let's just quickly jump back to that other one. I'm not going to use it because it's much more work. We could use this. C, we know epsilon naught, we know E, and then we could actually solve for B using that one, but that's a bit more work. And that relationship comes from C equals E over B. So technically there's two ways to do this. Isn't that fun? Isn't that exciting? But we'll take the easier option. Because why not? C equals E over B, and then the last one, pretty straightforward. C equals F times lambda. You don't even have to do parts A and B to do part C. Yeah.
You can use the other one either if you don't have the intensity.
Yeah, because, so the question was, can we use the other one even if we don't have intensity? We can, because intensity equals all three of these, which means they equal each other. So even if we don't have this relationship still holds. And these relationships just have E and B in it and a bunch of constants, which are totally things we have. So, yeah, it's a great question. But the way we go from this one to this one is C equals E over B. So that's why they both work. Anyway, back to wherever that problem is. C equals F lambda. So I'm going to go ahead and take all this stuff. At this point, there's not really anything exciting going on. I'll rearrange this for lambda. Lambda equals C over F. Step 4 is just putting numbers in and plugging them into a calculator. So I'll do it because it doesn't take that long, but it's the least exciting part of the process in my opinion. It's the part that, especially these equations, I have the utmost confidence everyone in this room could plug these in, but I will do it just so you all can check these answers. Make certain they line up with what's online as well. So we're something for E. So E equals 4e to the minus 3 over 0.3, which I'm not going to try to do in my head. 1.33. Again, it's not worth the potential for making a mistake. Yeah, so 1.33 e to the minus 2. And we remember our units of electric field because we have awesome memories in this classroom, way better memories than I do. And if we don't, that's okay. Paper has a wonderful memory, and this will be on your paper. So then we just take that and we divide those. 1.33 e to the minus 2 divided by, I didn't rearrange that one. We want to get for b, so let's go ahead and B equals E over C. I'll let you do the algebra to prove that that is true. I just multiply the B over, divide by C. 1.33 e to the minus 2 over 3 e to the 8. We're going to get a very small number, which makes sense because magnetic fields are always much smaller than electric fields. That's what this ratio tells us when it comes to light. Minus 11 Tesla. And lambda equals 3 e to the 8 over 1. I don't need a calculator for this one. I feel fairly confident in my abilities to divide by 1. You get a very, very long wave, which is why this would be very hard to measure. Yeah. Lambda equal over here. C equals F times lambda, rearrange, lambda equals C over F. Yeah, that's a good question. All right, so good application of a few equations we covered and a throwback to something from test 1. Fun times. All right, so getting into the meat of things, most of the problem set problems are actually going to be on refraction. Refraction is kind of what we'll be covering about today. So if you already started the problem set, you probably saw you can only do like problems 1 and 2, maybe 3 or 4, but the rest of them are mostly refraction, which we will cover today. So I wanted to mention electromagnetic spectrum. I've been talking about it, but it would never show, like I didn't have a nice picture of it. So here it is. I told you all that light is not just what you see. It's not the visible light. That is a very tiny, and this is not to scale at all. I'll kind of point out some numbers here. Radio waves are light, are electromagnetic waves. Gamma rays, microwaves, infrared, visible, ultraviolet, X-ray. You do not need to know the names of these, nor do you need to know, basically you don't need to know what it is. Let's just put it that way. I'm telling you all this because it is useful knowledge for you all outside of this class, especially as med students. There's some things I can kind of point out that will be useful for you, but they're more conceptual, and I'm not going to test you on that. I don't expect you all to have this written down, memorized, taking up space, whatever. It's not worth the space. But I do want to talk about it so that we can say we've seen it. Remember, so frequency, these are all wavelengths here. Frequency is down here. The ones with a high wavelength are on the right side of the visible spectrum. Ultraviolet and onwards. Why is this relevant to you all? Those are the ones that actually cause damage to the body. Everything to the left of visible is passing through your body right now and you have no problems with it. Every radio wave, every cell phone signals are in the microwave spectrum, every Bluetooth signal. You all are all emitting infrared light right now because you have body heat. Body heat is emitting infrared. All of these signals are passing through your body right now. They're all around you. How do you know that to be true? If the cell phone tower's over there and my phone's on the other side of me, I can still get a cell phone signal. Does that mean the cell phone signal is weaving around my body? No, it's passing through me. Radio waves are the same thing. I could have a radio under this, whatever. It's going to pass like anywhere around me, and it picks up the signal because that radio wave is passing through my body. So all these things on the left are interacting with you all the time. Hopefully, you are not interacting with X-rays and gamma rays all the time. Well, you wouldn't be alive if you were. Everything to the right of visible, we get ultraviolet. That's what the sun emits. Ultraviolet rays, that's what gives you a tan. That's where I'm sure you are familiar at this point. If you tan too much, you are at a higher risk of skin cancer. Why? Ultraviolet rays have more energy than visible light. They have a little bit more energetic than that. They're more likely to damage the DNA molecules, cancer cells, so on and so forth. X-rays, even more energetically, more energy to them, even more dangerous to you, hence why you wear the lead vest, limit your exposure. It is not dangerous to go get an X-ray. It is dangerous to have prolonged exposure to X-rays, hence why the doctor leaves the room when you get an X-ray, because they're giving X-rays all day, every day. So that'd be a lot of exposure for them. There's a safe exposure to all these, just like it's not bad to get some sun. It's not bad to get an X-ray. Gamma rays, it's bad. Yeah, if you get a name out of gamma rays, that's no good. And those come from like nuclear bombs. So again, you shouldn't be experiencing gamma rays anytime in your lifetime, God willing. So I wanted to mention these real quick just to show you that light is all of these things. Give you a sense of scale. Radio waves can go up to 10 to the 3, which is about 1,000 meters. Gamma rays are 10 to the minus 12. So that's a decimal, and then 12 zero or 11 zeros, and then a number. That's how small they are. So these waves have a huge frequency to them, or a huge range to them. And why are they defined this way? Because someone decided. This is all man-made construct. Like, where do you put the lines here? There's no hard and fast line for this, which is why I'm not testing on it, because not a huge deal. But I did want to talk to you all about this because it's important to kind of know that they different types exist. You may wonder real quick, I'll point this out, microwaves. You may be like, a microwave is dangerous. I should not go inside a microwave. You are correct. It will cook you. That is not because microwaves carry a lot of energy. That is because microwaves are at the resonant frequency of a water molecule. So they're at a very specific frequency, that is the resonant frequency of a water molecule. Resonance means when you hit resonance, something will start to vibrate with that frequency. More and more and more and more. Think about pushing someone on a swing. You're not just pushing constantly, that does jack squat. You push when they get to you, you let them go, you push again. There's a frequency to that pushing that makes it build and build and build. Microwaves have the resonant frequency of water, so the water molecules will vibrate more and more and more and more, makes heat, cooks things. You're made of water, you cook too.
I read that the first use of microwaves was in World War I, and they were trying to intercept enemy signals.
Okay.
And accidentally, one of the soldiers melted.
Yeah.
So that's when they realized that it can also heat up food and melt food.
Yeah, I mean, that's interesting. I haven't looked that up. That's a lot of, there's a decent amount of science discoveries that are by accident. And there's lots of things that have come from military funding that have had other applications. Yeah, I'm not super surprised with that. Microwaves are the cell phone signals as well that you all have. Thankfully, those aren't at the resonant frequency of water, so you're going to be okay. But
is it true that the reason why you can't put something dry in the microwave and nothing will happen is because, like you said, the water molecules is what?
Yes.
There's no water in anything that's dry, so it just stays dry.
That's why your hot pockets have the molten center and not as hot exterior. There's more moisture inside of a hot pocket than the outside. So things that are wet will heat up quicker than things that are dry in a microwave. The more moisture content, the higher it'll cook. You can get water pretty hot pretty quickly. If you put it in a microwave, the only thing you have to be careful of is you can do something, I forget what it's called, where basically you get it a little bit above the boiling point, and then if you touch it, it violently starts to boil. Whatever. It's okay to microwave water. Just do it carefully because it can get too hot, and then it'll be stable, but not actually. If you touch it, it'll whatever. You can look that up in your own time. But yeah, it does a real good job at cooking things with water, and everything you all eat has water in it, hopefully. All right, this is just a quick thing to show the relationship as wavelength goes up, frequency goes down. So this just kind of ranks them, and as I already mentioned, the energy's highest in the bottom. I have this clicker question. Yeah, we'll give it a go. It's free points for you all that are, again, I'm not going to ask a question on this as a test because I don't want to waste your note card space with something like this. It's not really worth it. But it's interesting. Which of the following has the highest energy? Ultraviolet, infrared, visible, or microwaves?
Professor?
Yeah.
I think your stream died.
Oh, such is the nature of things. Let's see. Huh? Oh, it did. Well, it thinks it's alive. Yeah. Goodbye, stream.